Welcome to a hydronic balance update and review seminar. It'll be a two-part seminar. It's going to be basics. We're going to start with basic hydronic balancing, why you do it, where you go with it, and a little update on codes and what may be happening with it. So this is the outline we'll follow today, and again it will be a two-part, 2 hours roughly, and we'll do about half of this today down to a pump and pedal trim example, part 5. We want to take our time and cover the basic fundamental things, because the key to future hydronics are going to be good balance, good energy efficient systems, and none of this cannot happen unless we do the balance correctly. So take a quick look at ASHRAE 90.1 2010 and 2013 and kind of talk in terms of what it might have, what impact it might have on things. First of all, if you're taking a look at this and kind of getting a feel for it, ASHRAE has been working with some of the balancing people in an attempt to make sure that they're all in agreement. And what's happening, if you deal with this a little bit, is NEB, one of the big ones, not pushing NEB so much, but they all are in agreement that balance is critical today and in the future, and they're talking a lot because some of these balancing procedures and codes and all need to be practical, need to be ones that can be commissioned in the field. And the bottom line is, through all of this discussion between ASHRAE and NEB and the other balancing agencies, it's very simple. Buildings today that we do a good balance on, we got to benchmark that. And we may very well have to come back in the future and recertify that balance to keep them balanced. It's kind of a simple concept, but if you got to lead a building, a green building that's very energy efficient, how do we keep it that way? So this performance measurement thing, which is a part of balance, a part of commissioning, it's going to be a huge discussion in the future. And many of you probably already heard about it, but it's going to be much more discussed as we go down the road. So let's talk a little bit more about where we're going, what's happening, and the future of balance. And basically what's happening is ASHRAE is working with NEB. We're trying to get the balancing procedure started. Now, what does this all got to do with ASHRAE is very simple. These ASHRAE energy codes, and particularly the Energy Standard 90.1, is a long-term attempt by ASHRAE to drive us to net zero energy buildings. That's the whole concept. And what's really gotten active has been ASHRAE 90.1 2010. Now, DOE looked at 2010 way back in 2013 and made the decision that by October the 18th, 2013, that every state in the country per DOE should have an energy building code equal to or better than ASHRAE 90.1 2010. Now, on the bottom of this screen, you'll see a place you can go to see where your state may be today. My last count, I believe, was about 13 states were there, and they're coming on rapidly all the time. The point being is, now what? ASHRAE 90.1 2013 is out, and DOE looked at it on September the 26th, 2014, and as you can see on the bottom, instructed or requested that every state have an energy code equal to or better than standard 2013 by September 26, 2016. Now, what all this means to you is very simple. This energy thing is going to get stronger and stronger and stronger. Yes, it may be moving a little bit slow with some states. It's not going to go away. Energy code's going to rise. It's going to be everywhere. It's going to get stronger every single day. And just sit back and watch. What does this mean to us with balance? But the first thing we got to look at 90.1 2010 and 13, what does it say about pump head? Because, see, pump head is directly related to balance, directly related to energy usage. And we want to make sure you understand the connection, because we're going to be looking at pumps as we talk about balance. We're talking about hydronic balance today, not air side, just the hydronic side. So basically what was new in 2010 was that every pump, you had to calculate the pump head and the critical path in that building and find out where that critical path was and count every T, every elbow, every fitting, and that becomes your pump head, and you got to put it in a file. So that means you need to know where that critical path is, and that becomes also extremely important when you start talking about balance. What does it say about balance in 90.1? Interesting. It says, and here's a statement in red, might be important to you to understand, that it's required. It's required on system B balance on any building over 5,000 square feet. And, you know, 5,000 square foot building is fairly small. And if you had a hydronic system in a building of that size, you'd have to have a balance that's done. And read a little bit further, the report has to be turned over to the building owner. So you engineers listening are going to have a balancing procedure in your specification. You're going to provide instrumentation for that, and it's got to be instructed this balancing report to be turned over to the owner in order to meet ASHRAE 90.1. So I got asking myself, looking at this, what does 90.1 say about what do we use to balance with? You know, that's kind of a basic question. So I went to the user's manual. Here's some actual questions and answers right out of the 90.1 2010 user's manual on balance. And the question was to ASHRAE, what types of balancing valves does the standard require? Bottom line is the standard doesn't specify to the engineer what he uses to balance. It just says you must balance, you must proportion balance, you must have a report. But here's some typical products or items or things you can use to balance with. And the first one you see is a calibrated balancing valve, which is the old concept. If I know the pressure drop across the device, I can take the CV of that and come up with a GPM. Old-fashioned balancing valve that we've had for years. Next item was a flow limiter. Some people call these automatic balancing devices. They really are not. They really are just plain old-fashioned flow limiters that if I specify a specific GPM and order this device at that GPM, it will not let the flow go over that GPM, that flow limit. Anything below that is doing nothing. So basically the flow limiter is set for a max flow rate in GPM, which is fine. The third item, which I did not put in red because it's a PT balance, a pressure temperature balance. And you can do some balancing with PT, but it's not going to be that accurate. And I just don't think it's going to be satisfactory to you. You can do it. It's a good check on the other three, but it's just you need more than a PT balance. And that's just my personal opinion. You can do what you want to, but that's my personal opinion. Third item is pressure independent control valves, PIC valves. Yes, pressure independent control valves are mentioned in ASHRAE 90.1 User's Manual as a possible way of balancing because they have a constant pressure drop across them. If you know the position of the valve, you know the flow rate in GPM. Therefore, you may see more people using PIC valves as a way of balancing particular situations. So let's just keep looking a little bit further and say, here's some typical pictures of what these animals look like, and a lot of various vendors are involved in making these types of devices, but they're there on the market, readily available. A lot of them, these old core lookup packages to give you something you can specify and make sure you got the instrumentation that you need to balance your system. How about balancing commission? Why do we keep talking about balance and energy? And real simple, it's more critical than it ever has been before. If you look at the ASHRAE's drive with 62 and 90.1, 90.1 is an energy code trying to drive the efficiency to the bare minimum. 62 is IAQ. They're trying to make sure the air is fresh, it's clean, it's comfortable. So the two kind of go against each other a little bit because on one side you're trying to make sure you got as much air as you need, which takes more energy and is comfortable. On the other side, energy. So you got to balance the two. You got to commission systems to make sure you don't have too much air, to make sure you got the right amount of air, and to make sure they're balanced. So the whole message is it's critical that we commission buildings and we balance them going forward to make sure that we got the proper balance of energy being used. So what does that mean to you if you're in the balancing business? Systems are changing. The old constant flow systems are gone, and they're a variable flow system. We're trying to take advantage of diversity. You're going to have to educate yourself. You can be involved in the business, in the balancing business. You need to do some system education. You need to understand every day. You need to read and learn the new hydronic systems, how they're being piped, what are the critical pieces, and you need to start understanding it a little bit. And a very simple thing is probably the most important advice I could give to you young people today would be to make a simple system sketch. Not every piece in that whole building, but just make a system sketch. How many boilers, how many chillers, how many pumps, simple sketch. What are you trying to do? And you'll see that as we go and why I'm pushing that concept. Last but not least, we're going to have tighter pump heads, tighter cooling loads. We're not going to have the old fat we used to have, so we got to make sure that we do these things right because the systems are being designed tighter and tighter to get less and less energy usage. At the same time, some of the controls are getting more complicated. So it's more critical than ever you understand what your system looks like and what it is. So let's look at some typical systems and ask you what your balancing goals might be. So 2 ways and 3 ways? Yeah, I think you need to stop and think about what's happening over the last 25 or 30 years. We've gone from the old 3-way valves where we just looked at constant flow to 2-way valves to vary the flow. That means we're going to put the water where we need it. What does that mean to you? Let's look at a simple concept called diversity. And if you're going to balance a system, you best understand this, or how will you balance it? It's a real simple concept. Let's say we've got a central chill water plant with a dorm with a 1,000-ton load, cafeteria with 1,000-ton, library with 1,000-ton, and a gym. So if you add up the individual loads, it's 4,000 tons. But if you run a block load, look at all those 4 buildings at any one time, and the peak block load of those 4 buildings is 3,000 tons. Now, by my definition, that's a diversity factor of 0.75. What that means is the kids can't be one place at the time. So where are the kids? So you start looking at this, okay, each individual building might need 1,000 tons of cooling, but if I look at the whole campus at one time, all I need is 3,000 tons. So how many chillers are you going to put in? You're going to put in three 1,000-ton chillers for 3,000 tons total, or 4 1,000 tons for 4,000 tons total, and we're not going to play the old game of standby. So real simple, here's your question. Real simple little sketch. I like simple sketches. Diversity is 0.75. How many chillers are you going to put in that plant? And how are you going to handle those peak loads? Now you got to begin to think about balance. So if I had 3-way valves, the old constant flow, I'd have to have 4 chillers. I'd have to pump at 10-degree delta T, 9,600 GPM, to pump the flow rate the same. I'd have the same flow rate all the time. If I went to 2-way valves, I can put variable flow, only put the water where I need it and when I need it, and get away with 3 1,000-ton chillers. And that's why 2-way valves and energy-wise have come into play. Here's the old-fashioned way, 30 years ago, constant flow, 3-way valves, and you see the flow rate was 9,600 GPM in this chiller plant. So if you're trying to balance this campus, it's 9,600 GPM. You got 2,400 GPM each dorm at a 10-degree delta T, 2.4 GPM per ton, and you got constant flow. So you're going to give the dorms in the cafeteria, each building set, 2,400 GPM, whether they need it or not. So you're wasting a lot of water, and you got to have those 4 chillers. Now, as soon as I go to 2-way valves, I drop back to 3 chillers. I drop my main back from 20 to 18 inch. I drop my total flow rate back from 9,600 GPM to 7,200 GPM with 2-way valves. Man, I'm saving a lot of first cost. I got a lot of good energy savings going on. But now, how do you balance? You begin to get the point. The point is the total flow through the distribution is going to be 7,200 GPM. Yet you go to that dorm, you got to set it up for 2,400 GPM. You got to set up the cafeteria for 24. So you best know what you're doing here. Your total flow to distribution is only going to be 7,200, but you got to be able to give each building 2,400. And that's what I mean by having a simple system sketch and understanding the intent of the engineer, understanding what you're trying to do. How else can you balance this? If you don't understand that, there's no way you could balance this. And this is why it's important you begin to take the system concept in mind and understand what it means to you. So if I start looking at system concepts, there's basically 5 basic systems available that you need to work with. And I think the fundamental building block has been primary, secondary. We can play with it a little bit and talk about it. Let's just take a quick look at the various ones. Here's a traditional primary, secondary piping setup. Constant flow through the chillers, the little green pipe is the decoupler, and you see the secondary pump with 2-way valves. Traditional, primary, secondary. Fine, good system. Here's primary, secondary, tertiary. And you see the little green common pipe at the chiller loop, the green in each building. I got 3 sets of pumps, primary, secondary, tertiary, to take advantage of diversity. All I'm asking you to do is recognize the system. I'm not saying any of these systems any better than another one. On primary, secondary, tertiary, and this seminar is not intended to spend a lot of time on the subject except to tell you they're easy to balance everywhere there's a common pipe. Everywhere there's a bridge is easy to balance, primary, secondary, tertiary. These are some of the reasons or advantages you might want primary, secondary, which is another whole seminar we get into. The point of the day is you recognize what they are. Let's go a little step further. and make sure you understand. Here's a combination, primary, secondary, tertiary. And I say combination, look at zones A. Zones A are closer buildings to the chiller plant, and there's no tertiary pump. Look at zone C. It's the furthest one out, and it don't have enough differential pressure from the secondary pump to pump zone C, so we had to put a tertiary pump. We had to put another bridge out there. The point of this discussion is recognize a simple sketch is required for you to understand how to balance zone A, zone B, and zone C. Otherwise, you don't have a chance of balancing. And this would be called a primary, secondary, tertiary, kind of a hybrid. Here's a zoned pump. I got rid of the primary pump, and I've got an individual pump in each building pumping the distribution piping out, distribution piping back. This was called zone pumping or distributed pumping. If you go to ASHRAE book, you'll see them in the journals, and they're defined for you. I'm asking you, before you try to balance a building, to sit down and make this simple system sketch to know what the intent is of the design. Otherwise, there's no way you'll ever get this thing balanced properly. So, some zone pump comments, and again, the intent today is just let you understand what they are, not to try to go in detail about each one. Here's another picture of a good example of a zone pumping situation. And you kind of get the concept that each individual loop has its own pump to be balanced, which is entirely different than true primary, secondary. So here's the comments again about good places for it. How about variable primary flow systems? We get a lot of people talking about those today, where we've got one set of pumps pumping through the chillers and all the distribution. Variable primary pumping. Same thing on hot water, same thing on chill water. Now your balancing issues are entirely different again. This shows two pumps in parallel with a pants leg connection between the two in this particular situation. And you see these pumps again are pumping through the chillers and our boilers all the way out to the distribution pipe and to the very end. Again, make that simple system sketch if you're going to balance these so you understand. So if I kind of summarize, and this is important, very important if you're going to be in the balancing business, you should be able to recognize these 5 basic systems and make a sketch before you set out to balance the job and know what GPM you need at each building and understand why. Primary pump we just talked about. Primary, secondary, by the way, primary, secondary pumping is beginning to use variable speed on the primary and variable speed on the secondary. You're going to begin to see a lot of that coming. Primary, secondary, tertiary, tertiary hybrid, where you got a little combination of both. It's important you catch that you see this. There's nothing wrong with that design. In fact, it's a good design. Where the building's closest to the chiller plant may not need an extra pump. And then primary, secondary, zone pump, the distributed pump. So my message is learn these basic concepts, and if you're going to balance a job, you're going to be the guy in charge. You got to know what's going on, and these are the basic fundamental building blocks you're going to find for hydronics. Let's go to basic balancing a little bit 101. And we got to do this because you've got to understand the fundamental things involved after you pick your systems. So let's see what we got. I'm going to use the system sizer, and I'm going to ask you, and I'll show you in just a few minutes, if you don't have the old-fashioned Bell & Gossett system sizer, which is freebie, go online to your Androids or to your Apple applications and download it to your cell phones. It's a freebie. You need to have it available. If you don't have it available, you might go get it right now and put me on hold if you've got it recorded and come back and play with this. I'm going to refer to scale 5 several times in the next few minutes as we go through this. And again, I'm encouraging you to go get a hand wheel, the old-fashioned hand wheel if you're like me. I love that. Or you go download this freebie to your cell phone. Just go to Bell & Gossett applications for system sizes, and it'll be available to Android, Apple, and get it in front of you so you can walk through this. If you're going to do balance, you're going to play with hydronics, you got to understand this basic concept of balance. And we're going to work through the fundamentals as we go and come back to scale 5 of the system sizer, and I'll refer to it a couple of times as we go. So here's the fundamental building block of all balance. Nothing proprietary, just a law that we gotta go by. If I double the flow in GPM, my head goes up 4 times, it goes up by the square. If I cut my GPM in half, my head is 25%. In other words, the difference in pressure drop and flow is the square relationship. So as I double the flow, my pressure drop's got to go up by the square. And that's what scale 5 is on the system size. It's nothing but that square relationship to allow you to do balance. Every balancing thing in the world you play with is based on that fundamental scale 5 system size. Now on the plastic system size, the handheld is for specific gravity of 1, specific heat of 1. If you go get the Android version or the other version, you can correct it for other specific gravities. But for water, we use 1. For chilled water and hot water and go on, we're fine. What I'm asking you to do is understand this basic formula. We're going to be playing with this for the next 30 minutes. You need to get it in your head that every balancing device out there, every CV, everything out there with hydronics, it's based on this formula, which is pretty basic. Here's a picture of the Apple version, and the Android looks very similar. You go online and download. And again, it gives you the information I just gave you. But I think you might be interested in this. It also has PVC pipe sizing in it, which is something everybody's looking for. It's available in Spanish and English and other versions of it. It also has metric. In other words, you can do all your calculations in English and all metric and hit a button, switch them back and forth. And that's kind of the way I do things anyhow. If somebody wants metric from me, I do it in English and I hit a button, spit out the metric and give it back to them. That's great to have. Also handles, as you can see, other fluids other than water. Specific gravity is 1, but if you've got a different fluid and you know the specific gravity and the specific heat, you can plug it in here and it will take care of that for you. Last but not least, if you work with circuit setters, the CVs are in here for the circuit setters as well. So you probably want to go get this because it's a freebie and I use it about every day. There's also an updated Windows-based version of the system sizer, as you're seeing here. It's a picture of it. And again, it has the Spanish language built into it, multiple units of measurement, different ways to use pressure, feet, pounds, whatever metric terms you want to get into, and ASHRAE 90.1 support, which we will talk about another time. But basically, it allows you to come in and pick a pipe size and do a detailed pump head loss calculation, just like ASHRAE called for, print screen and keep it. So you got all those things you could do with this. Again, it's a freebie. Go online, download it. It's not a product. It's something available to you. It's a design tool. Every engineer needs a good design tool. This is one you really, really want to have. So let's go back to the scale 5 or the square function thing we talked about. We talked about if I double the flow rate, my pressure drop's got to go up 4 times. If I cut my flow rate in half, my pressure drops 25%. And I'm not trying to insult you, I'm just trying to get you familiar with that and what that means to you from a balancing standpoint. And that's all in the world at scale 5 on the system sizer is we talked about. Or take your calculator out. If you got one hand, you don't want a system sizer, just plug in that function and see where we go with that. So here we go with a pump. I got a base mounted in suction pump here. I got a flow rate through this pump of 701 GPM. I have installed on this pump a calibrated balancing valve, which for us is a triple duty valve. And there's your pipe size, and there's your model of the valve. Now, the question would be if I know the pressure drop through this device when it's wide open, and I'm not going to change the position of it, is 2.31 feet at 700 GPM. How can I come up with a pressure drop at 1,000 GPM? And I like to add this to the conversation without calling anybody. You should be able to do this. You should be able to take the little formula I taught you a few minutes ago and say, wait a minute, what do I know? I know the pressure drop at 701 GPM is 2.31 feet. What would be the pressure drop at 1,000 GPM? From that square relationship, that's all we're asking you to do. Now, if we have the system size, so we go to scale 5, and we just plug in, what do we know? See the 700 GPMs at 701. By the way, 2.31 feet is a pound, and so you see pound on the bottom of the system size where it says CV1, that's pounds. At the top is 2.31 feet at 701 GPM, so now we know the setting. We know that at 701 GPM, the pressure drop is 1 pound, 2.31 feet. They don't change anything. Go with the 1M, which is 1,000, and you see your pressure drop now is over 2 pounds or 4.6 feet roughly. If you have the Android or the Apple-based version, it'll give you the number directly reading out directly, if you like it that way. So here we go. I just figured out that at my 1,000 GPM, my pressure drops 4.7 feet. Now I could go ahead and keep that same setting, not change the setting I got on my system sizer, and add in these other flow rates. Now remember, I told you that if I double the flow rate, my pressure drop should be 4 times. So let's just see now. I got 701 GPM is 2.31 feet. What should it be at 1,400? Should it be just about 4 times that? And sure enough, that's what it is. Now I've got all those pressure drops and off of my system sizer from that one setting because it's fixed. That formula was, if I know the flow rate, I know the pressure drop. If I got those two numbers, I can give you the flow rate and or pressure drop any other setting you want. And that's all I've done here. And I constructed the characteristics CV-wise of this valve. By the way, the CV of this valve, in case you hadn't picked up on it, was 701. And most control people will give you the CV. So if any piping or equipment, if you know its pressure drop at a GPM, you can calculate its pressure drop at any other GPM just by knowing that. For that reason, that fundamental statement of law, all you manufacturers publish CVs. And the CV is nothing more than the flow rate through their device with a pressure drop of 1 pound or 2.31 feet when the specific gravity is 1. That's all a CV is. And when you get a CV of a valve or a CV in any piece of equipment, you can get a CV of a chiller. Anything you know the flow rate of, you can get the pressure drop. And the flow rate at 1 pound a drop is the CV of that device. So I'm trying to jump ahead of my little self, but that's what a CV is. And if you need to kind of get this in your mind, because this is a fundamental building block of balance again, you need to understand this and what a CV is and why it's important to you. So here we go. 1 pound, 2.31 feet, specific gravity 1, the flow rate, that's the CV of an animal. So go back to my triple duty valve. The actual flow rate at 1 pound, which is 2.31 feet, is 701. So the CV of my triple duty valve, and wide open in this particular case, is 701. And you can find that CV of any valve, any animal out there that you want to play with, and use it, and use that information to make a balancing valve out of it. So combination balancing valves, by the way, we believe you need about 3 feet of pressure drop across a wide open valve to make it read accurate. In other words, if you get your pressure drops too low, how good can you read a gauge? How good are you? If you're accurate reading gauges, fine. But we believe that if you get down below 3 feet, a 1 pound drop, it's going to be tough to read a gauge accurately. The more accurate your gauge reading, the more accurate your flow reading. It's that simple. So you can handle the problem with better instrumentation. Let's go back to the scale 5, that formula we talked about on a system sizer. Let's use it as a flow meter. What am I saying? Here's a little simple sketch of an old-fashioned system with 3-way valves, and I got a chiller on it. Let's say that it's a 916-ton chiller. Let's leave it at 10-degree delta T. Let's leave it at 2.4 GPM per ton. Those are the old numbers we want to use. I got 2 pumps running in parallel, no big deal here, but I'm flowing at design flow per the chiller manufacturer, 2,200 GPM at 23 feet of drop. What do we know? The chiller vendor, the chiller manufacturer told us that the flow rate at design flow of 2,200 GPM and the pressure drop was 23 feet or 10 pounds. 2.31 feet make a pound. So 23 feet of drop would be roughly 10 pounds of pressure drop through the chiller when I got 2,200 GPM of flow. And remember what we just taught you about the square function. So you say, wait a minute, Chris, if I know this, the tubes are clean, we've got to assume the tubes are clean. Yes, we'd have to assume that. But assume the tubes are clean, and we know this, then we could give you the pressure drop at any other flow rate. Or we could give you the flow rate if we know the pressure drop. Wow! Are you saying to me I can make the chiller barrel into a circuit setter or a flow meter? Yes. And this is what's neat when you start learning some of this and putting it together. So let's do that little game. Let's assume you're involved. Let's say you sold the pump. And the owner calls up and says, the system's noisy. System's noisy. We're not getting what we got, get enough flow. Everything's wrong with the system. Flow rate's short, all these things. And you don't really know. You're sitting in your office. And the owner calls and says it's short of flow. how would you know what the flow is through that chiller without leaving your office? What would happen if you said to the owner or to the owner's maintenance man, you got any pressure gauges on your chiller? Obviously, hopefully they do. And you said to the owner and or the maintenance man, would you mind doing me a favor before I come out there and give me the pressures in and out of that chiller? Now, we already know from submittal, you got submittal laying in front of you, that a clean chiller would have 2,200 GPM at 23 feet of drop or 10 pounds drop. You already know that. So my question to you is, what is the pressure drop across that chiller now? Now, first of all, we're going to take a pressure reading with a gauge going into the chiller and a pressure drop with the gauge coming out of the chiller. In this case, the pressure going in is 43. The pressure coming out is 32 pounds. So the pressure drop is 11 pounds. Now stop right here. For everybody involved, that's a pretty tight reading of 11 pounds. I want you to take that reading with the same gauge. We would have a gauge on the inlet and the outlet of the chiller, or we should. I'm pretty sure your detail shows that. What I'm asking you to do is take that reading with the gauge on the inlet side, take that gauge and move it to the outlet side. Take the gauge on the outlet side and move it to the inlet side. Double check this. I am not interested in whether it's 43 pounds or 32 pounds. I'm interested in the pressure drop. All I want is an accurate pressure drop. I don't care what the actual pressure is. I want the pressure drop. If you make that reading with the same gauge, if the gauge reading out a little bit, you get rid of it because it gets subtracted. In this case, I would switch them and use both gauges, same side, for same readings, and hopefully I'll come up with an 11-pound drop with both sets of gauges. This is critical to you because a gauge can easily be reading a pound or two high or low. And when you move it and take it with a second reading, you get rid of that error and you get a much more accurate reading. Now, that out of the way, let's assume 11 pounds was accurate. Can we not go to scale 5 of the system sizer and come up with GPM now? Let's try it. So what do we know? We know it's 10 pounds of drop at 23 feet at 2,200 GPM. We know the pressure drop's 11 pounds. So scale 5, you can do it on your little Android or your Apple versions or on the hand wheel, which is the old-fashioned way of doing it. Let's just show you a picture and see what we get. So if we go and read on that, we can set it up at 2,200 GPM at 23 feet or 10 pounds. And we go to 11-pound reading and read our flow rate. And what you will see is 2,300 GPM. Now, 2,300 GPM, I'm going to show you next the setup. Real simple on scale 5. I know what? 2,200 GPM is a pressure drop of 10 pounds. And if you look 2M, pounds on the bottom scale there, you see the 10, the next one over is 11. That would be the flow rate that we know what it is. We know at 10 pounds is 2,200 GPM, but my actual pressure drop per the gauges was what? 11 pounds. So at 11 pounds, what am I reading? I'm reading 2,300 GPM. So my answer is my pressure drop's higher than design. Design was 10 pounds, and I'm up to 11 pounds. And so I say to the owner, you're not short of flow. You got 2,300 GPM. We're fine. And I just proved it. I just took the chiller barrel and made it into a flow meter. Isn't that interesting? Now, I hope you understand you can do this with anything. You can take any two-way valve, any pressure drop any known pressure drop in your hydronic system and make a flow meter out of it. Absolutely. And you got yourself a good start. I would like to next take the same formula and apply it to system curves a little bit and get you a little up to speed on system curves and what they are and how they work, because it's the same set of concepts. It's the same little formula. Back to basics. So what is the system on a pump? It's everything from the discharge flange to the suction flange of the pump. That's considered the system. And if you start looking at system, there's going to be some flow rate and some pressure drop involved in that piping. And that's a fixed, once you do this, that's a fixed set of piping for that pump. And when you change the position of the two-way valve, or you change the position of the throttling valve, you're changing the system curve. But when you start it up and you get it running and you get everything fixed, you've got a fixed system curve, and it's not going to change until you change position of the two-way valve. So we want to look at the system curve, its impact on balance, its impact on flow, and how our pump relates to that, and horsepower and energy. Remember, this is all about energy and energy usage. So let's go back to a little scale we had before. Let's look at a pump. Let's do a little system schedule and see what we come up with. It's just a typical little sketch, same system we had before. And we know in this particular case that our flow rate was going to be 2,200 GPM and the pressure drops 100 feet ahead. Okay, so now we know from design, engineer calculated a pressure drop through the critical loop here. He calculated the three-way valve, the cooling coil, the return piping, the air separator, the suction fuses, service valves, tributary valve, chiller, calculated everything. Detailed loss calculation. He came up with 100 feet of pressure drop at 2,200 GPM. That's what he specified his pump for. That's what the pump was purchased to do. The pump was purchased to do 2,200 GPM, 100 feet ahead. Remember that function of system curves. Let's go back to that same little formula again. If I double the flow to a given system, then the friction loss is going to go up 4 times. In other words, if I double the flow in this thick system from 2,200 GPM to 4,400 GPM, the pressure drop's going to go from 100 feet to 400 feet. It's going to go up 4 times because of that square function. And now I'm beginning to calculate and produce a system curve. I can take that same logic and go the other way. Take the 2,200 GPM and cut it in half to 1,100 GPM, and my system friction loss would be, pressure drop would be 25 feet. If I cut the 1,100 GPM in half again, 550 becomes 6 feet. So you're kind of beginning to see how the system will perform on its system curve based on the flow rate through that system. And that becomes your system curve. Now let's talk about this a little bit. I hope this formula looks familiar to you. We're asking you to learn to plot a system curve. Is it not the same formula as we just showed you before? You see how important it is to get this basic fundamental building block comfortable with you. Why you need the system size, or why you need to understand if I double the flow rate, my head's at 4 times, cut the flow rate in half, my head is 25%. That's a fundamental thing we've got to get involved. We're going to keep the same little number. We're going to go back to our example of 2,200 GPM 100 feet ahead. We're going to go to our system size of scale 5. It can be the hard copy, any one you got, and you see I've got it marked here at 2,200 GPM at 100 feet ahead. I'm going to fix it. I know that point. And once I know that point for my system, I can give you the flow rate and head at any other set of conditions. I just leave it fixed. I read them all off, and this is what I just did. And you see how it follows that half, fourth. You see how the square functions work. So now I have the system curve for your system where you did the calculations and you told me it was 2,200 G per 100 feet ahead. I can tell you the pressure drop at any other flow rate. And now I take this and I come up and I plot a system curve. So there's my system curve. That's unique to your job. Valves wide open and fixed, unique to your particular situation, your school, your hospital, your pump. That's unique to you. But it shows you the pressure drop at any other flow rate. And that's what's important to you to understand if we're going to do balance, and we're going to relate the pump to balance and start bringing this all together to see how we can save some money. So the next thing we're going to do is we're going to take this system curve and we're going to put it on a pump curve. How much flow will a pump give my system? You bought this brand new pump at 2,200 G per 100 feet ahead. How much flow will it really give my system? And a very simple statement to you engineers. Remember the first law of thermo? Energy in is energy out. The energy you put in something, it's got to come out somewhere. So from a pumping standpoint, and here's a little pump curve. From a pumping standpoint, the pump impeller line, this pump itself, puts energy into the system. The system curve takes energy out. So first of all, when you buy a pump, you're going to get one size impeller. Yeah, I can change the speed of the pump, which we can talk about later, and in effect change the sizes of the impeller. But once I got a specific speed going, whatever the speed may be, I'm going to have one impeller size. And that one impeller size is where you buy it from the factory. In this case, we got a little blue line. I think the impeller size is a little bit over, what, 11.2 inches or something like that. And I think you see that it's been picked for 2,200 GPM at 100 feet ahead. It's been a point we picked it for. Now, I got this pump picked. Where's the pump going to run? The pump's going to run where we put that system curve across it. In this case, the system curve, we just plotted it. And we just see where the red star crosses the impeller curve is where the first law of thermo comes in. Pump energy in from the pump has to be energy out from the system curve. So there's only one place that pump can run. That's where that system curve crosses the pump curve. It can't run any place else, period. I don't care what's going on, it cannot run any other place. If you did it accurately and you got exactly your requirement 100 feet ahead, you'll be at 2200 GPM. If you overheaded your pump or you didn't have the right pump head, you will not be there because that first law of thermal is going to apply, and it's going, the system curve, wherever it crosses the pump curve, is where it's going to run. So you kind of got that in your head by now, I hope. Let's take some of these basic things we have learned and look at pump impeller trimming, why it might be important, how you would do it, and how it fits into ASHRAE 90.1 and balance. See if we can bring some of this together for you now. So let's do a pump impeller trim example. I've got a pump here, it's a Model 4 BC, doesn't matter, but the pump has been specified and purchased and submitted to do 650 GPM at 76 feet ahead. And that 76 feet ahead by ASHRAE should be the critical circuit, remember? And if we say the design point was 650, you're telling me I need at a full load 650 GPM. I don't need 800, I don't need 750, I need 650. Will satisfy this job. I don't need to pump any more than that because the more you pump, the more energy you're wasting, remember? And I need 650 GPM, and I've calculated pump at 76 feet ahead. So that's what we got. Now, everybody understand this, and we're going to go back to a system curve. We're going to see how we're doing. We're going to start talking about balance a little bit here. So here we go. There's the pump. That little red star is the pump you purchased. That's the pump engineer specified. That's the one everybody says we need. We need a flow rate of 650 reading straight down to the bottom. Horizontally, you see the flow rate is GPM on the bottom. Vertically, you'll see it in meters and in feet of head. In this case, we're looking for 76 feet ahead going off to the vertical axis. Perfect. By the way, we're about, what, 83 points of efficiency. Not a bad-looking little pump. Okay, great. That's what's specified. That's what we got. That's what's on the drawings. Now, you put it in, and you get a call from the owner. Get a call from the client. He says, my pump is noisy, or my pipes are noisy, my pipes are making a noise, a little high whistle noise going on. Could be air, but could be some other issues as well. But you got a complaint. So you're going to check it out. Why could you possibly have noise in a pumping system? One possibility would be over pumping. But let's just take a look. So let's go to our pump, and let's look at suction and discharge gauge readings again. I like to take them with the same gauge. I know we got individual suction, individual discharge gauge is fine. But when I want an accurate differential pressure across my pump, please take that with the same gauge. If you got two gauges, take it twice. Take them individually with the same gauge because, again, what am I after? I'm after pressure drop. I'm after the actual pressure drop. Let's turn it around. Instead of saying pressure drop, I'm after the pressure the pump's generating. I'm really talking about pumping the pressure up here. So what is the actual pressure the pump differential the pump's putting into the system? What is it generating? So if I go to this thing and I look at the suction side, and I look at the discharge side, I'm coming up. Our pump is generating 63 feet ahead. I took the same gauge, it was in PSI, and I divided by 2.31 feet per pound, and I see my pump's generating a differential pressure between the suction side and the discharge side of 63 feet. And the specification was for what? 76 feet. See the 76? But I'm only doing 63. Now what does that mean? Does that mean I'm underperforming? No, it doesn't. We have to flow in GPM, not head. So if I got a fixed impeller size, which I already bought my pump, that's what I showed you a little while ago, what would my flow rate be? Now, first of all, we would recommend you use some kind of a gauge, common gauge, so you can get differential pressure with one gauge. This particular gauge, by the way, for a specific gravity of 1 has feet of head built into it for you, which makes it easier for sometimes for maintenance people to understand and read versus PSI. Because all your pump curves are going to be in feet of head, and most of your gauges are going to be in pounds. So if you want to go back and forth, if you can assume that specific gravity is 1, like for water, You can buy a gauge that's got feet ahead already built into it and make it easier for everybody to find your 61 feet. But let's go to a model again. First of all, the yellow star is an impeller size of 9.5 inches. That's what you specified. That's what the engineer had. And that's supposed to be 650 GPM at 76 feet ahead. Fantastic. But you had a complaint of noise, and you asked for the differential pressure across the pump. Now, you can't change that impeller size. And right now, let's have a fixed speed. Let's don't play the speed game yet. We can bring that in later. Be happy to, but not yet. We're going to be constant speed at the point we are right now. If my pressure drop is 63 feet versus 76, what is my flow rate? I'm not underperforming flow-wise. I'm overperforming. So you see the red star? The yellow star is design. It's where you thought you'd be. The red star is where you really are. And if you take the red star on that impeller of 9.5 inches, that's where you got to be with 63 feet to the vertical axis. Read straight down. What is your flow rate? 850 GPM. So you're flowing 850. Only requirement was 650, and that's why it's noisy. You got high velocity going on. You've got a noisy system because you're overflowing. How would you balance this system? What's involved? A little bit further common solution to this would be to go to that triple duty valve, a combination valve, and throttle back on it to force the head back up to 76 feet and force it back to the required flow rate of 650 GPM. Let's see what that looks like. Red is where we're running. The green is where we want to wind up at flow-wise. So we could throttle the triple duty valve or throttle the balancing valve. A little yellow line should get you back up there. And I've added pressure drop to the system. I've changed my system curve. My system curve was actually 63 feet, but I'm going to add some pressure drop through it by going through this throttling valve. I'm going to push it back up to 76 feet. Now I'm at 650 GPM. I'm now back at design. Great. Did I save any money? Well, a little bit. It's 6 cents a kW running constantly. I just saved $600 a year. Dropped it from 17 brake horsepower back to 16, and I've got design flow. I'm giving the engineer, I'm giving the owner exactly what they asked for. 76 feet ahead, 650 GPM, and I've saved $600. Did I do a good job? No, we did a lousy job. We broke the law. We didn't meet ASHRAE 90.1 2010. Why did we not meet ASHRAE 90.1? Let's go back to balance. Go back to our hydronic balance statement here. Hydronic system should be proportionally balanced in a manner to first minimize throttling losses, then pump impeller shall be trimmed, or the pump speed shall be adjusted to meet designed flow. What does all this mean? All this means is if you did a true proportioning balance, then the valve would be wide open. It wouldn't be throttled. If we trim the impeller, we could reduce the horsepower. If you didn't want to trim the pump impeller, we could put a variable speed drive on it and slow it down, and we're reducing horsepower. So what we're after is operating costs. On the bottom line, this is an energy code. We're trying to reduce energy. And that means we don't want that combination throttling valve being throttled back. It's nice to have it around, but we don't want it throttled back when we wind up with a true balance. So let's go back to our example. So we're now back at the green point because we throttled it. We went to 650, 76 by throttling. Is there a better way to get to 650 GPM? That's all we need. We don't need 850. Is there a better way to get to 650 GPM in this particular example and save more money, save energy costs, which is what we're really after, is reducing energy to the bare minimum? Let's take a look at that. The first thing is, what is the actual system curve? Not what was specified. What was specified was 650 at 76. We're not there. We turned the pump on, the discharge valve was wide open, and we read 63 feet at 850 GPM. Don't change any valves. That's what the real system is doing. You know, pumps are stupid. Systems are stupid. They don't read the specs. And this pump is actually putting 850 out at 63 feet ahead. So that's the true system curve the way it's installed. To be fair with everybody involved, you never know how a system's going to get installed. You never know whose equipment you're going to get. So a pump estimate is an estimate. In the real world, they're going to come out differently than you put on your drawings because every system is probably piped differently by different contractors, different pieces of equipment. So it would not be unusual to be, in a different point. But the real system curve here is 850 at 63 feet. Let's go to scale 5. 850 at 63 feet. Remember that? Right off the CV curve, right off the square function curve. Let's pull off the points for a real system curve, not the one on the drawings. So we know it's 850 at 63. So let's just pull them off. So at 750 it's 49, 650 37. So we just did that square relationship. You can pull it off your little iPad or however you want to do it, off your system size of scale 5. And we're going to come up with the system numbers. These are the real numbers based on your gauge readings, the 63 feet ahead. Now what do? We very simply take those and we plot them onto your pump curve. I'm going to plot them right now in red. There you go. So the red line with the red stars is the real system curve, the one that's really happening and giving you 850 at 63. The green line was what you thought was the theoretical system curve. It was going to give you 650 at 76. But the bottom line is we don't need 76 feet ahead, do we? What's the goal here? Don't forget your goal. Your goal is to balance. Your goal is to get you to 650 GPM. That is your goal. We don't need 850. And we don't need to throttle back on it to get to 650, do we? We need to trim the pump impeller. We need to trim this pump impeller. What size do we go to? How do we get to the size? Right now we're at 9.5 inches. And if we don't throttle back, we're going to throw 850, which we don't need. So what do we need to do? All right, just don't throttle anything. You tell me what flow rate we need. I think it was 650, right? So all we got to do is come along and say, okay, we're really running on that red curve, but not on the other one. Our real system curve is 850 at 63. Now all I really need is 650 GPM. See that vertical line? All I got to do is strike a vertical line up at 650 and see where it crosses my real system curve. And it crosses, help me out there, somewhere about 7.5 inches, something like that, maybe a little less. We'll figure out exactly in a minute. But that's a new impeller size that we need. Look at the horsepower. Horsepower is down a little bit over what, 7.5? Wow. We dropped the horsepower way down. We leave our throttling valve wide open. If we trim that impeller, to the proper size, what happens cost-wise? Well, the little orange star is where we need to be. By the way, I can do the same thing with a variable speed drive. I can take it to that point and trim the impeller electrically by just slowing the speed down. But if I trimmed it, it'd be to 7.6 inches versus original 9.5. So if I pull the pump impeller out of the pump and trimmed it to 7.6 or slow it down, that's where I'm going to need to be. And let's look at some numbers here. I like numbers when you pull all this together. This is extremely critical you get this last slide here. In other words, I was running at $8,000, 17 brake horsepower when I just turned it on. If I throttled it with a throttle valve, I could push it back up to the original design point of 650 GPM to 76 feet ahead, and I dropped it to 16 brake horsepower. And your cost now is $7,400. I saved $600. But when you did the right thing, engineers do the right thing. When you did the right thing here, you did a proportioning balance. You want to make sure that throttling valve is left wide open, and I trimmed the impeller down or put a variable speed drive on it. I was able to cut the horsepower down to 7.6 brake horsepower, operating cost down to $3,600 a year. I cut it from $8,000 to $3,600 a year, but doing the proper balance, proportion balance versus ASHRAE 90.1 2010 Energy Code, and I still got my 650 GPM. I'm still giving you exactly what you asked for to begin with. And this goes on, ladies and gentlemen, on every job. I was on a job the other day. I cannot tell you where it was. It was an extremely large chill water plant. And I was walking through with some of the senior people, and they were asking me, what are some things we can do to save energy? Over 90% of the pumps in their buildings had throttle valves closed, partially closed or throttle back on. First simple thing, they need to go and trim pump impellers, maybe buy new pumps. You might notice that as you keep coming this thing down here, you see the new operating point here, the green. If we had much more extra head, we might have fallen off the pump curve. So in some cases, it might be better off that you buy a brand new pump for new pump condition to get the efficiency back up. The bottom line is ASHRAE 90.1 2010 and the proper balancing procedures are going to lead you to pumping better trims or slowing the speeds down, because there's a lot of cash here to be saved.